So in today's class, we are going to see how we can have suppression of causal anomalies through a three valued logic. So we are going to use the freedom of statements which can be implicated from the logical relations and the truth table which is constructed thereof. The one novelty being we just also included, apart from truth and false as a this thing, we also included indeterminate something which can be equally taken as one of the pillars as the other two. And in the process, we arrived at various relations. So we will continue with that, just how the limitation of Bohr-Heisenberg thing, like once we measurement, the value is only assigned after measurement. So there are some limitations to it. So before, how can see how can obviate or bypass the causal anomalies via quantum mechanical interpretation via this three-value logic. How causal anomalies can be suppressed is not suppressed, you can do away, or if he has chosen the phase suppression, you can see that description can be somehow it need not to be there in the first place. So before we are going to say, so we can have in our interpretation, for example, a disjunction of uh, this is disjunction. So we can have some relations, disjunction of A can be there, which is to be seen there. So disjunctions of A, which is double cyclical negation. So it is so this is a complete negation. So this is a cyclical negation. So A disjunction means cyclical negation of B. So this tends to cyclical negation of B twice. Once it will come B and again it will come B. So this means disjunction of A with cyclical negation. So you can say the statement leads to, so we will not either have B neither have B in this thing. So this statement will lead to negation of A and B, complete negation of A and B, which in turn means that it's a sort of tautology. So it's a sort of, you can say, statement which can not be disagreed with. And so implication one guarantees that complementarity statements cannot be both true. So now what we are going to see is that we can have other statement. B disjunction of minus B implies C. We cannot construct a we cannot construct a disjunctive statement derivation of statement C by showing that C is that both is true both when B is true and when B is false. So we cannot construct a disjunctive derivation of a statement C to show that C is true when both B is true and B is false. So it's a we cannot construct a disjunctive. So B disjunctive of minus B, B disjunction of something which is not B. This implies C. So you cannot construct a derivation of a statement C by showing that C is. So C cannot. You cannot construct a disjunctive derivation of the statement C. We cannot. So you cannot construct C by taking B and B, not B simultaneously. So this is it. So from this, you can say. So you can see from three-valued logic, you can construct a statement. We can construct a disjunction of a statement which can be true and false, because one of them will lead to intermediate. In case of two-valued logic, you cannot construct a statement. One of the statement is true, and you cannot construct a statement which is in conjunction with true and false in that simultaneously. That's it. So this is how we can differentiate two-valued logic from three-valued logic. That we can construct a statement and we can have a disjunctive of that statement which can be true and false, while in case of two-valued logic, it may not be the case. So in two-valued logic, C is proved when B disjunction of B bar means B bar means negation of B implies C. So analog in three-dimension, three-valued logic is B disjunction of B bar is implies C, or B disjunction of B implies disjunction of B. It is cyclical negation of B implies C. So B disjunction of cyclic negation of B. So disjunction of cyclic negation of B twice. So it will give B. So it implies C. So we are constructing B. This is cyclic negation of B. This is cyclic negation of B twice. It will come once again and it will come back. So that implies it's C. It belongs to C. Is demonstrated. So which has the implication of tautology. The way we have this statement. It's a tautology. So B is true, false, or indeterminate. B is true, false, or indeterminate. All the three. So now we have to see the other thing, other part of it. When is a statement true? So we'll have another thing, something called complete and close. Something called complete so a disjunction is called closed when a disjunction is called closed in case n minus 1 terms are false and nth term must be true. So a disjunction is closed if we are just a true, false. So n minus 1 term is false and the next term after the n minus 1 it comes out to be true. And a disjunction is said to be exclusive if only one of the terms, one term is true and other terms are false. And the third one, a disjunctive statement is said to be complete if one of its terms must be true or what is seen. So in exclusive one of the terms is true, the other are false. In complete one of the terms must be true or what is the same or what is same. So the disjunction is true. So what have these three things to do with what have these three things to maybe so what have these three things to do with? So we can say, for example, for two-valued case B1, so this is equivalence is B1, B2, B3, B2, B3 sine and Bn. So it's equivalent to, so B2 naught, so it's not B2 naught, it's not B3 naught. So B is not B2, B is not B3, B is not Bn naught. Or B2 bar is, B2 is this is B1, B1, B3, so on and so forth. And Bn can be B1, B2 bar, Bn minus 1. So that a disjunction for which the relation holds, so that's it. So now it can easily be shown a disjunction B1, disjunction B2, disjunction Bn must be true. In other words, a two-valued logic, a two-valued disjunction which is closed is also complete. So a two-valued logic which is closed is also complete. So in closed, we said that n minus 1 statement is false, and term is true. And complete means one of the terms will be true. Yes, 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 yes. So B1 is not equivalent to B2. Yes, you can say. So in two values logic, we can. It's simple. It's closed and also complete. So now we can see what's the difference between two valued and three valued logic. For example, we cannot derive the consequence of the disjunction. B1 disjunction, B2 disjunction, Bn disjunction. Disjunction is indeterminate. So in three valued logic, we must be able to distinguish between in three valued, we must be able to distinguish between closed and complete. So before coming to how we can see how three value logic just obviates the need for causal anomalies, so we should be able to distinguish between the how the operations of how we define closed and complete vis-a-vis three-valued logic in relation to two-valued logic. So what are its how we can have those things, for example. So in three-valued logic, to say a bit, closed disjunction need not be complete. So how you can show it, the closed disjunction cannot be complete. So you can have for a three-valued cases, for example, for a three-valued case, a closed and exclusive disjunction is given by B1 minus B2 minus B3 minus Bn. B2 is minus B1 minus B3 minus Bn. So for in case the n minus 1 term is true, so false, this is true. For a statement to be closed, and for a complete one of the statements may be true. So you can see here there is the idea of equivalence is there. Equivalence. You can go from B1 to B2 and B2 to B1. So this equivalence may be alternative equivalence or it may be strict equivalence, which depends the thing. So if it's alternative equivalence, so once you come from this to this, it's not always possible if you go from A to B and B to come back. So it can be restrictive sometimes. So alternate equivalence is not equivalent to an equivalent statement. So how? So B1, B2 minus B2 minus bn minus 1. So it's bn. So b1 goes to minus b2 goes to b minus b3 goes to bn. b2 goes to minus b1 minus b3. Yes, yes, b3 minus bn. Sorry, and bn goes to or comes back b1 minus b2 minus bn minus 1. Yes, yes. So in a generalized form, in which n slits are used, so closed character follows when you disjunction follows when we use implication from right to left, right to left. You can have closed character. This to this, this to this, this to this. And exclusive character follows from when you go from left to right. Exclusive. B1 is different from B2, B2 is different from B1, Bn minus 1 is different from B1. So now the question is in three-value logic, it may be, disjunction may be closed but need not be complete. Means that this is bn minus 1 is false, this is true. It may not be case, the sequence. So you can say that we can say that the disjunction is a special case of, this is a special case of closed and exclusive disjunction. So how does it say? So B is not a disjunction of minus B. Minus B means negation of B. B disjunction of which is not B. So you can say it's corresponding to the proof. So B1 disjunction of B2 disjunction of B and implies C. So the distinction of close and complete disjunction eliminates causal anomalies. So it's how does it So we can have its analogy with, if you remember, slit experiment. Once we studied causal anomalies. For example, if we had the way Young's double slit experiments were there are n slits. So light can pass from one slit, still you will be able to have a diffraction, the impression of those spot or bright and bright diffraction pattern from one pinhole. Or you can have n pinholes. So you will not be able to distinguish whether the interference, the patch, the spots which you saw on the screen. So if only one hole is open, still you will get the pattern. But if you will be able, there are n holes or more than one holes, so you will not be able to distinguish the impressions which you had from the screen, which holes or which hole or holes, which mean more than two, the impressions or could be due to. So if you closed one or at the expense of other, so we have to we have to compromise with causality to explain things that the impression on the screen may not be necessarily from more than one holes. So how can that thing be taken in account of by this tedious value of three-valued logic, which has a property of being closed and complete distinction. Complete disjunction being closed and complete distinctions. So what we say is that relations in 9, relations in 9, so if it's 9, it's not, we cannot maintain, disjunction is disjunction is complete or true. All we can say is that it's not false. So it can be indeterminate. It can be indeterminate. Disjunction is complete or true. Disjunction is complete or true. It's complete or true. Complete means the penultimate element is false. This is true. It's complete or true. That's fine. It's complete or true. So once it's not false. No, it's not false. Yes. So it can be indeterminate. Yes. So if it's both complete as well as true, it may not, the distinction may not be false. So it can be, so you can have this intermediate, indeterminate as a, its truth value can be indeterminate. So again, the example can be, for example, 1 silt, 2 silt, 3 silts. So it's n minus 1 slits will have some impression on the screen. So there may be n silt. One of the silt will also create some impression, diffraction or dark or bright spots. But if we close the slit here, there are n minus 1 slits. They will also produce that interference pattern here. But the point is whether the impression was created by n slit or n minus 1 slits in that sense here. So if n statement is true, this statement is this true, n minus this impression may not be created by this in that sense. So you can, the logic can be taken in that sense of closed. That in closed thing we have that one of the n minus 1 statement may be false, this may be true. You can have this analogy here. So it tantamounts to this statement. It's complete or true. If the particle has been observed at one slit, we know that particle did not go through others. Then the disjunction is also true. Yes, this is the analogy. Or the disjunction 9 may be intermediate if our knowledge of relations holding between the statements B1, Bn will not be intermediate, will not be indeterminate, but true or false. For n is equal to 2, the relations may be simplified as B1 can go to B2. So it's equivalence. So B1 is can go to not a B2. Not a B2 can be 1. In the reverse, it can be alternative equivalence. Or B2 can be here, it can be minus B1 can be here. And strict equivalence can be there if you can have B1 is equivalent. So it's a stricter statement of diametrical negation or diametrical disjunction. So now how we have to relate entire of this to what we are doing or what we have been studying. The thing is that the thing is that probability of A, B1, B2, distinction of A, B1, B2, distinction of to B and C. So this is a formula or, so for example, probability of particle leaving the source A, and passing through the slits, which were slits B1, B2. So these are n slits B1, B2. So if it is not passing through B1, it's not passed through B2. So we don't know. So the impression created here may be due to this slit, this slit, this slit. It may not be not this slit. So n slits. So A is the source. These are distinctions, disjunctions arriving at the C, arriving at the point C. Is given by formula like sigma I is 1 to n. Probability of A into Bi, probability of A, Bi, C, I is equal to 1 to n, A of Bi. So we can only be applied when two statements A and B1, B2, Bn are true. We can show that B1, B2 cannot be proved true. So from this, so we have formulated things in such a way that statistical pattern which occurs at the screen when all the slits are open simultaneously is superposition of individual patterns, resulting only when one of the slit is open. However, we have these two statements, this or true. So now A is true since it states that particle came to T. So we cannot prove this statement as a source, or if these slits are open, cannot be proved as true. So therefore this statement is not applicable if all slits are open. So this is a contrived sort of reasoning which is applied, that if probability of A as a source, and these are n slits, and we can have disjunction. It has not, the light has not, if it has gone from source, if it has not gone from source, it cannot be due to this, it cannot be due to this, it cannot be due to this, whatever. So we somehow can exclude the possibility that this thing. So because we saw that B1 intersection of B2, disjunction of Bn cannot be proved true. Therefore, it's not applicable if all slits are open. We see that no causal anomaly is derivable. So this is one of the ways of, I think, so to me, this I don't really see. So at least in this class, we have tried to see how we can formalize this statement that the use of three-valued logic can somehow can the thing of these causality paradox, which comes once we have corpuscular interpretation, where we don't know once light comes, if we take this analogy of these quantum particles as waves as well as particles. So if there are waves, so we cannot pin down the effect of the superpositions at a given point, whether it's due to one slit open or other slits open. So it can be paraphrased in this language of three-valued logic. So from here, it becomes, the statement becomes more clear in the sense that when we divide n small intervals delta q1, delta qn, so we relation 8 holds, this holds. So that disjunction is closed, disjunction is closed, although it need not be complete. The statement is not translatable, so the particle is at one and only one point at the interval this. The fact later consequence cannot be derived, makes it impossible to assert. So you cannot derive this statement, the particle is at one and only one point of the interval delta q. So we cannot assert causal anomalies from this thing. So other part of it is that once we have, for example, we have this tunneling as a phenomenon, how we can account for it. Here also in this thing, how is we can account for this tunneling is that the probabilities of small number of particles to tunnel a certain barrier, even though we can just explain it from decay particles of certain elementary particles, the probabilities may be small, uncountably small, but that small if we take into account. We can explain tunneling as a phenomenon. But here also the explanation seems from three-valued logic is that if we use a restrictive interpretation by three-valued logic, the causal anomaly cannot be stated. How? Uh, so if, for example, principle requires that if we have sum of kinetic and potential energies be constant, it connects the simultaneous values of momentum and position. So if one of the two is measured, the statement of other entity remains indeterminate. So it follows that the principle of conservation of energy is eliminated by the restrictive interpretation. So you can do away with principle of conservation. We need not to have principle of conservation if we have three-valued statement by saying that this as a quantity here becomes indeterminate. So total energy of the system is indeterminate. So whether it's finite, whether it's infinite, we don't. So it's indeterminate. It's open-ended. So in that context, you can just jump the potential barrier. So here this is a peculiar way of interpreting tunneling or doing how we can explain anomaly of tunneling via this interpretation of logic. So I don't know whether this thing has suppressed or causal anomalies, but the language of it gives us freedom in the choice of language, in the choice of logical relations to explain things, not necessarily by virtue of two-valued logic, which can be somehow seen to be most closer to the classical logic of the classical world, not quantum mechanical world. Full stop.